This lesson on graph theory starts with some definition of terms, and then I'm going to talk about connectivity, minimum spanning trees, and traversing graphs. Connected graphs were introduced in a previous lesson. In this lesson, graph connectivity is explored in more detail. What I want to do on this first slide is define some terms, going from the most general to the most, or at least more specific with more requirements. So we'll start with a walk. A walk is a finite alternating sequence of vertices and edges. So in other words, alternating means you have a vertice and then an edge and then a vertice and then an edge, where each edge connects the preceding and succeeding vertices and where the vertices and edges may repeat. So the key thing here is you can have the vertices appear multiple times in a walk, and you can also have edges appear multiple times in a walk. All the other concepts I'm going to define here are walks. I could have drawn another square around trails and put walks, but I'm kind of running out of space. So the next level down are trails. So all trails are walks. A trail between vertices U and V is a subgraph of a graph G consisting of edges and associated vertices that lead from U to V. Vertices can be repeated in a trail, but edges may not. A trail is written as an ordered sequence of vertices where there is an edge between each adjacent vertex in the sequence. If U equals V, in other words, if the start and end vertices are the same, then the trail is said to be closed. Otherwise, the trail is classified as open. A closed trail is also referred to as a circuit. So these two boxes here, sort of the light orange and the green, they can constitute circuits. And there's a subdivision of circuits, which I'll get to in a second. But first I want to define paths. So a path is a trail. A trail is a walk, with the added restriction that the vertices may not be repeated. So here, the path, you have distinct vertices and distinct edges along the path, other than the two endpoints, which could coincide. If the endpoints of a path are the same, then we have a cycle. So that would be this box in here. And then if you just have the endpoints being the same, and then you don't have this added restriction of the path where the vertices are not repeated, then you would have a circuit, but it would be not a cycle. So that's this box here. And I think that's about it. As depicted in the Venn diagram, all cycles are paths. That's this here. And all paths are trails, which I said, but not all trails are paths. You can see that here. The paths have that additional restriction. Okay, so a lot of terms to kind of get a straight. You may want to actually do a screen capture of this page just to have it on the side as you read further on, so you can refer back to which one of these definitions I'm talking about. But the key idea is that you start with walks, then trails are a little bit more restrictive than paths. You can't have any repeats at all. And then these two things, there are two types of circuits, cycles and non-cycles, basically depend on the starting and end point being the same. We have a few more definitions on this slide. We talked about these in the lesson on examples a few lessons back, but I want to go over them again just to get all our definitions together in one place. So a circuit, i.e. a closed trail, as we discussed in the previous slide, and a connected graph G that contains every edge of G is called an Eulerian circuit, named after the famous mathematician Leonhard Euler. An open trail that contains every edge of G is called an Eulerian trail. A connected graph is classified as an Eulerian graph if it contains an Eulerian circuit. So I want to go through some of these different concepts here and using this example here, graph G, I also note here the length of a trail is the number of edges in the trail, not the number of vertices. Okay, so I'm going to draw on the graph as we go through this. So we'll look at the first one here, P, A, B, F, C. So that's a path from A to C. You notice there are no repeated vertices and no repeated edges. Let me erase that and go to the next one. So C1 is A, E, F, B, A, A, E, F, B, A. So that's a cycle of length 4, and by definition all cycles are also circuits. Let's go to the next one. All right, then we have a longer one here. G, H, E. Oops. G, H, E, A, D, H, I. Okay, so that was a complicated one. So this is not a path because we have the repeated vertex edge. When we went around here in the loop, we repeated this here. So we have a trail, but we don't have a path in this case. And the length is 6. It's just counting, again, that will just be counting the number of edges. Okay, let's go to the next one. Then we have D, A, E, H. So D, A, E, H, G, E, D. So you can see we came back to where we started, but again we have the problem of, let me point to it here. We have the problem vertex E is repeated. So it's a circuit, but it's not a cycle. Let me erase that. And then we have one last thing to mention here. The graph G is not Eulerian since it has multiple odd degree vertices actually. For example, H, D, F. And we had a theorem going back to the lesson on examples, which I restated here. A connected graph has a Eulerian circuit if and only if every vertex is of even degree. So clearly that's not the case here. Okay, let's continue. On this slide I have a couple of concepts related to connectivity. The first concept is a bridge, and that's basically an edge that if you remove it you have one or more graphs from your initial graph. So I have a couple of examples here. On the left, we have two bridges. If you remove this edge here, CF, then you would have a graph C and then everything else. So you would have two disconnected graphs. And if you removed HI, again, you would have two graphs. One would just consisting of the vertex I and then everything else here. So that's a graph with two bridges, but we can remove the bridges. Let's see if we can draw on this. So if I put an edge here, and let's say an edge here, then this graph would no longer have a bridge, or hopefully I'm correct on this. I don't think there's any single edge. No, I don't believe there's any single edge that you could remove from this where you would have two disconnected graphs. All right, so let's remove that. And then on the right we have another example. There's several, well there's one bridge here. If we remove CD, then you have one graph here and another graph on this side. And there's this alternate definition for an edge to be a bridge. An edge is a bridge if and only if it's not contained in any cycle. You notice I said cycle here and not circuit, because every circuit contains at least one cycle. You may want to give a shot at proving this. I'll give you a hint. If you go back to the last lesson, classification of graphs part 2, I had a theorem number 6 towards the end of that lesson, and there was a diagram in there that was very close to what you would need to prove this theorem. So you may want to try that as an example. Okay, then we have a second concept that's similar to a bridge, except that now you remove a vertex and all the edges adjacent to the vertex. And if you have two or more disconnected graphs in that case, then that's called a cut vertex. So we have a few examples of cut vertices in these two graphs down here. So in the graph on the right, B, if you remove B, and then of course you would, using this definition here, you remove all the adjacent edges. So you remove this edge, this edge, this edge, and this edge. Then you would have two disconnected graphs. Same thing for C. If you remove these three edges, then you would have this graph in here and this triangular graph here. And the same thing for D. You would have just this edge is one graph, and then all of this here is the second graph. So you have three cut vertices in this graph on the right. On the left, I don't think there are any. You may want to give it a try. Let's see. I guess, no, actually there are, because if you remove F and the three edges attached to F, then you have a single graph C here, and then everything else. So that would be F would be a cut vertex. And if you removed H and the associated edges, you would have a graph with just one vertex, and then everything else that's left. I think they may be the only two. You may want to explore that to see if there's any additional cut vertices in this graph here. Just to make clear what you need to do to remove a vertex in terms of determining whether or not it's a cut vertex, I have an example of that here. So we again use this graph, which we've seen a few times now, and we'll remove E, vertex E, and the rule is you remove all the adjacent edges, which I've done here. And you notice we still have a graph that's connected. It's just one graph. So that would tell us that E is not a cut vertex. So far, all the graphs we talked about have the edges with weight 1, or basically the edges all have the same weight. But there's a lot of examples where you would want to put a weight on the edges, as I'm pointing to here. So for example, BD has weight 7, and I have a weight on every one of these. So some examples might be roads. You know, maybe this is how far they are apart in terms of distance. It could be how long it takes to on average cross a road, or even at a given time of day. It may be telecommunication lines. So these numbers could represent the capacity. You know, maybe 1, even though it's a longer distance, 1 indicates how much the bit rate over this line here, and then maybe this line here has a bit rate that's 7 times greater than that. So you would put a different number or weight on the edge. So what I want to do is take this example and work through some of the details on the next few slides. I carried over our graph from the previous slide. Now I want to put some context to this. We're going to work on a particular problem. What we want to do is find something called a minimum spanning tree, which I'll describe in a minute. So assume the vertices in this graph here are telecommunications equipment, and this thing in the center, this light blue grayish, is a pond. So we can't go, for example, from F to C directly. We would kind of go, maybe make 2 steps here. And these numbers are the cost in putting the telecommunication lines between the different equipment. So, maybe 5 is fairly high. So maybe there's some hills. We maybe have to go underground and do some digging. Maybe this one here, 1 is just a straight line. You already have the maybe telephone poles up, and you just need to connect another line to it, and so this maybe it costs less. We don't need to worry about those details. The main issue is here that you just have different costs between the vertices, and the vertices represent telecom equipment. And what we want to do is find a minimum spanning tree. So we want to be able to connect between all of these vertices, even if it takes 2 steps or 3 steps, at the minimum overall cost. And that means removing some of these edges. We don't need to have, for example, multiple ways of going out of G to A and B. We might just go from G to A and A to B, and not have this one here, this line here for it. That's I'm not sure that's part of the solution, but we'll see that when we go through the details. So just historically, there was first this problem was first addressed in 1926, and later on by another person, Kruskal, and that's the algorithm that's better known and what we're going to use to solve this problem on the next few slides. Kruskal's algorithm is summarized below. We'll first look at the general algorithm, and then we'll apply it to our example. So assume the algorithm is applied to the graph G, to a graph G of order n. So we have n edges. Sort all the edges in order of their weight. Start with an empty spanning tree, so we don't have the graph spanned at all when we first start. All vertices but no edges. Pick an edge x of smallest weight from the edges not in S, and which has not been previously discarded. If there is a tie in the terms of weight, arbitrarily pick one. If the addition of x to S does not form a cycle, update S to include x, else discard x. Keep track of the discarded edges, because we're not going to repeat those as noted earlier in the directions here. And then we keep doing this. Repeat step 3 until there are n-1 edges in S. So basically we're going to end up with a tree, which is given a name here, that's what you would expect, right? Spanning tree. So let's see how this works with our example. On this slide I have the algorithm applied to our graph. So this is the first step here. We'll go from the top left across and then down. This will be the final result here. So the first thing is we have 3 edges of weight 1. We'll just pick one of them. So we'll pick FD. That's our first step. You notice I kind of made the vertices a little bit bigger here once they're as part of the spanning tree. Then the next step, I picked another one of the edges of weight 1. That's this one here. Then there was a third edge of weight 1, AC, and I picked that. So far we're going pretty smoothly. You notice we don't have any cycles yet. If we have a cycle, we're going to have to discard that edge. So we've depleted all the ones of weight 1, but we have several of weight 2. So we'll pick this one here, EG. So these 3 edges form a path, and then we have another edge here that's not touching those 2. So we're still good. We don't have any cycles. It's a little bit hard to see here, but I picked another edge of weight 2. You notice I have a dotted line here. So It's a little bit hard to see because it's overlapping one of the outer edges. So that's of 2. And so far we don't have any cycles. However, the next one is a bit of a problem. So at this point we have edges ED, this one here, that's of weight 2, EF, that's of weight 2, and FA, that's of weight 3. So that would be the next level up. Now if you add any one of those to the spanning tree, you get a cycle. We can just look at maybe one of them. I'll let you check the other ones. Like ED, for example, you notice we have ED, DC, and then CE. So that would give us a cycle. And you have the same problem with these other 2. So we have to put these 3 in our set capital D that we mentioned in the algorithm on the previous slide. And we won't reuse those. So the next possibilities are GB and GF, both of weight 4. GB and GF. So we'll pick GB since GF leads to a cycle. So we'll pick GB. And at that point we have 6 edges, n minus 1, 6 edges, and our graph has 7 vertices. So now we have a tree. And I'll kind of remove all the edges we didn't use, and I'll show you the final result in a little bit clearer picture on the next slide. On the right is our spanning tree. I removed all the edges we didn't use. It's still a little bit hard to untangle here. What I did here is I took F and I pulled it out this way, and I took B and I pulled it out this way, and then you just had this AC sticking out. And so I could take this and draw it this way here. This is a little bit easier to see. So this is our spanning tree, and these are the weights. So this is a minimum spanning tree for our graph G. It turns out it's not the only one. As you notice along the way, there were certain points where we had several edges to select from, so that you could end up with a different solution. And in fact, in the last lesson from this playlist, I have a number of exercises, and one of the exercises gives instructions to pick a different edge somewhere along in the process, and then finish the algorithm and get a different spanning tree. So again, this is a minimum spanning tree. The minimum meaning the weights added together is a minimum. If you've been following along in these lessons, the very first lesson I talked about this Königsberg bridge problem. And in case you didn't see the first lesson, I'm going to do it again here. With the benefit of all the theory that we've developed along the way in our playlist. So for those who haven't seen it before, let me just quickly go over it. So this in white here is a river going through the town of Königsberg, which is now Kaliningrad in Russia, and you have these bridges here. So there's 7 bridges, and the idea was to start on one bridge and go through all the bridges without going over any of the bridges more than once. So that was the task. And there was sort of two variations, I guess. One variation is you would start somewhere and go across all the bridges, not crossing any of them more than once, and then return to where you started. And then there was an easier option where you started with in one area here, and you covered all the bridges, without going over them more than once, but you could end up somewhere else. So for example, you could start in region W, go over each bridge once exactly, and then maybe end up in this going over F last. Okay, so that was the problem. Then I'll explain how to put this in terms of a graph, and then I have a couple of theorems at the end that explain whether or not you have a solution for problems like this. So I've copied the bridge and the configuration from the previous slide here on the left. And then I've mapped it to a graph on the right. So let's just double check that. We have the vertices representing the areas W, X, Y, and Z. W, X, Y, and Z. And then the bridges are edges. So you notice from W, area W, we can get to X over either bridge A or B. We can get from area Y to X over bridge D or E. Go from area X to Z through bridge G. Then from W to Z, from here to here, is bridge C. And then finally you can go from area Y to area Z over bridge F. So we have this graph here. And on the next slide I'll give you the two theorems that we can examine to tell whether this is Eulerian and whether it has an Eulerian trail. And just to remind you, because we're going to need this information to apply the theorems on the next slide, this vertex has degree 3, this vertex has degree 5, this vertex has degree 3, and this vertex has degree 3. So all the vertices are odd for this particular problem. We have two theorems. I think I mentioned these earlier, but I'm going to go over them again. So a connected graph G, either a simple graph or in our case a multigraph, you notice we had multiple edges going between vertices, is Eulerian. In other words, it contains a closed trail that includes every edge of the graph, if and only if the degree of every vertex of G is even. So as we saw when we counted the degrees, in fact every vertex had degree odd. So it's not, our graph is not Eulerian. Then we have the second theorem. A connected graph, either a simple graph or multigraph, contains an Eulerian trail, an open trail that includes every edge of the graph, but you don't need to have the beginning point and the end point being the same. If and only if exactly two of the vertices have odd degree. In this case, the two vertices of odd degree are at opposite ends of the Eulerian trail. So again, we have 4 vertices of odd degree, so that means we do not have an Eulerian trail in our graph. And as we knew from the very first lesson, there was no solution to the Königsberg bridge problem.